Welcome, curious minds, to the deep dive. Prepare yourselves for a journey that might just, well, fundamentally challenge your understanding of reality itself.
Yeah, get ready for this one.
What if the most basic distinctions we make, like what's big versus what's small, or even the very nature of gravity, could be described in completely different ways?
Seemingly contradictory ways, even.
Exactly. And yet both descriptions would be absolutely undeniably true.
Imagine looking at the universe through, I don't know, multiple lenses at once.
Right. And each lens shows a distinct picture, maybe even an alien-looking picture. But every single one leads to the exact same truth about how things actually work.
That's the core idea we're tackling today.
Today, we're plunging into this amazing concept of duality in physics. And it's not just some clever theoretical trick, is it?
No, not at all. It's a really profound principle. It's where you have two utterly distinct theories, different mathematical frameworks,
Okay.
that somehow make identical predictions for physical phenomena.
Identical predictions. Think about that for a second. The math, the variables, maybe even the number of dimensions involved,
Can look wildly different. Completely different languages almost.
yet they end up describing the exact same underlying physics.
Precisely. It's like, remember that analogy we discussed?
Right.
Two profoundly different instruction manuals for assembling the same really complex machine.
Right. One might be intricate ancient hieroglyphs,
And the other, maybe compressed binary code.
Yeah.
Totally different logic systems.
but if you follow either one, you always build the identical working machine. Always.
That's duality in a nutshell.
So our mission in this deep dive is to really unpack what that means. Not just the definition, but, as a lens to view the universe.
We'll look at some famous examples, some frankly bizarre ones from modern physics.
Yeah, the kind of ideas that really reshape what you thought was possible. And then we'll go beyond the equations.
To the philosophical side, what does this mean for our idea of truth or reality itself?
And to guide us, we're drawing heavily from the insights in the article, The Duality of Physics and Reality. It does a great job distilling some incredibly complex stuff.
It really does.
Mm.
And it's precisely this challenge to our common sense, our intuition, that makes duality so compelling.
How so?
Well, our minds, through evolution, we instinctively seek a single objective truth. We want that one-to-one match between our description and what is.
That makes sense. Find the right answer.
But duality, right from the start, suggests maybe that's too simple, maybe even misleading. It forces us to ask if our very human-centric view of what's real or fundamental actually lines up with how the cosmos is built.
That's a crucial point. So let's start by really nailing down this core idea. Duality. Two completely different theories, same predictions. But let's dig into completely different, it's not just like different notation.
Oh, definitely not. Not just cosmetic changes. We're talking about theories built on entirely different concepts.
Okay, give me an example.
Imagine one theory describes reality using point-like particles hitting each other. Like tiny billiard balls, forces between them.
Got it. Very mechanical.
Then, its dual might describe the exact same reality using continuous fields, like ripples spreading on a pond. Or maybe even fundamental vibrating strings.
Wow, okay. Fields versus particles, that's fundamentally different stuff.
Different foundational elements, different math, different variables, even sometimes different numbers of dimensions.
Different dimensions.
Yeah. One theory might work in our familiar 3 space dimensions plus time. Its dual might need only 2 space dimensions plus time, or maybe something even more exotic. The underlying stuff and the rules look completely unrelated.
That is a huge difference, not just apples and red apples, more like apples and quantum foam, like you said.
Exactly. No obvious resemblance on the surface.
Yeah, and this is the mind-bending part. They make identical predictions.
Absolutely identical. That's the key, the non-negotiable part.
So no matter which theory you use to calculate something observable,
It's like the energy of a particle, or how fast something decays, or the gravity between two things.
both theories give you the exact same number.
The exact same
Big.
quantitative answer
Yeah.
every single time. It's not an approximation. It's a perfect mathematical equivalence in what they predict you'll see.
It's like those two computer programs you mentioned, written in different languages by different teams.
But input the same starting conditions, get the identical result, always. It's this exact agreement on observations that makes it a true duality.
Okay. And this is where the philosophical ground starts to shake, right?
Definitely.
If you have two distinct mathematical systems, two languages of physics, both perfectly describing the same reality, then which one is true?
It feels like a trick question, doesn't it? Or maybe just a really unsettling riddle. It hits right at the nature of truth in physics.
Is one the real description and the other just, I don't know, clever mathematical trick.
Or, and this is maybe more unsettling, doesn't it? Neither is fundamentally more true than the other. Our intuition screams for a unique, single reality and the one correct theory describing it.
Right. Science finds the truth.
But dualities suggest maybe reality isn't uniquely describable like that.
Yeah.
Maybe it allows for multiple, equally valid, fundamentally different descriptions.
So it challenges our basic assumption about what real even means.
Exactly. It's not just blackboard stuff. It hits our core beliefs about reality.
So it's less about reality being an illusion
No, not illusion.
and more about our description of it being non-unique. It's humbling, really. Suggests our intuition about one special description might be too narrow.
Precisely. Let's go back to that furniture analogy, but let's really push it like you suggested to capture this deep difference.
Okay, the bookshelf. Manual A, meticulous diagrams, pictures for everything, arrows showing connections, visual, intuitive, you see where things go, like our normal position space.
Right. And then manual B, it's dual. Pure text, abstract, algebraic, no pictures at all.
Just equations.
Equations, logic statements. Maybe it describes the exact torque for each screw, the vibrational frequency of the joints, the energy needed for stability, perhaps some weird topological data about how parts interweave.
So, completely different focus. Properties, relationships, not just spatial layout, like a momentum space or frequency space description.
Exactly. And here's the kicker you added. Manual A is written in, say, alien light patterns. You need special sensors, decoding algorithms.
While Manual B is in some ancient, lost human dialect, needs years of linguistic study.
Two vastly different symbol systems needing totally different ways of thinking to interpret.
Yet both reliably build that identical, perfect bookshelf. That's the level of difference we're talking about in physics duality.
That's the level. And crucially, neither manual is more correct or more real about the bookshelf itself. They're just different languages, different operating systems for the same physical truth.
You wouldn't say the alien light patterns are less real than the ancient text if both work perfectly.
Exactly. So this sets the stage for how physicists grapple with these much bigger dualities, where the bookshelf is the entire universe.
That really helps visualize it. Okay, let's leave the hypothetical bookshelf and dive into the real deal. Specific examples from physics. We'll start with one people might have heard of, but connect it to something deeper. Wave-particle duality and Fourier transform duality.
Right. This is foundational. Not just quantum mechanics, but signal processing, optics. Lots of fields.
Okay.
Any wave, ocean wave, sound wave, quantum wave describing a particle can be described in two fundamentally different yet mathematically equivalent ways.
Let me guess. One is our intuitive way.
Yes. The first is real space or position space.
That's our world. We see a ripple cross a pond, we track its position, its height, right here, right now. We locate things here and there. It's how we navigate.
Exactly. Our whole experience is rooted in position. But then there's the alternative, frequency space, or in quantum physics, often momentum space.
Okay, what's that like?
Instead of describing the wave by its amplitude at points in space, you describe it by all the pure frequencies that make it up and their relative phases.
Like breaking down a musical chord.
Precisely. You analyze a complex chord. You find all the individual notes, the pure sine waves of specific frequencies that create that sound. You're not saying where the sound is, but what frequencies it contains, how loud each one is.
So a wave's shape in position space, like how spread out it
Is inherently tied to its frequency content. How many different frequencies are needed to build that shape?
Two totally different ways to see the same wave. One where, one what frequencies, how do we connect them? You mentioned the Fourier transform.
The Fourier transform is the mathematical bridge. It's this incredibly powerful tool, an algorithm really, that lets physicists and engineers rigorously translate between these two descriptions.
It decomposes the wave.
Yes, it takes a function of time or space and breaks it down into its constituent sine and cosine waves of different frequencies. It shows you the wave spectrum. And crucially, it's perfectly reversible.
Go from position to frequency and back again. No information loss.
Exactly. A perfect mathematical duality.
And in quantum physics, this math gets very real, very physical, because the Fourier transform connects a particle's position to its momentum.
Precisely. In quantum mechanics, particles aren't just tiny billiard balls. They have wave functions. The Fourier transform is the fundamental link between the wave function described in position space and the wave function described in momentum space. It's not just math. It's about the nature of quantum stuff.
And here's where it gets really interesting for reality. This exact mathematical equivalence, this perfect duality, it directly causes Heisenberg's uncertainty principle.
It does. The uncertainty principle isn't some fuzziness added on top. It falls right out of the math of the Fourier transform applied to wave functions.
Remind us what it says again.
It says the more precisely you know a particle's position, the less precisely you can simultaneously know its momentum and vice versa. And it's not about bad measurements or clumsy experiments.
It's inherent.
It's an inherent property of the wave itself. Think about it intuitively. A wave that's sharply peaked, very localized in space.
Okay, a narrow pulse, precise position.
To build that sharp peak, you have to mix together a wide range of different frequencies. Many frequencies mean uncertain momentum.
Ah, I see.
Conversely, a wave with a very precise frequency, meaning precise momentum, like a pure musical note.
Yeah.
That pure wave naturally extends over a large region of space. It's spread out, its position is uncertain.
So the duality, describing a wave by its position, is perfectly dual to describing it by its frequency spectrum, its momentum. Both are equivalent descriptions.
But they feel so different to us. We live in position space.
Yeah.
That feels real. We walk around in it.
But physics says momentum space is just as fundamental, just as real.
Exactly. And this really starts to chip away at the idea that our intuition is the best guide to fundamental physics. It sets the stage perfectly for even weirder stuff.
Okay, let's do it. Let's crank up the weirdness. Moving from quantum basics to what's maybe the most celebrated, most active area of duality research today, especially in string theory, the add-SCFT correspondence. This one really does twist your brain.
Oh, absolutely. Add a CFT. The core statement is, well, it's deeply counterintuitive.
Lay it on us.
It says, a gravitational theory, a theory with gravity existing in a specific kind of curved spacetime called anti-de Sitter space, or 8S.
Okay, gravity in 8S space.
Is mathematically equivalent to a quantum field theory without gravity.
Wait, without gravity?
Without gravity.
Yeah.
Operating one less dimension.
Hold on. Let me process that. A universe with gravity, maybe in 4 dimensions?
Right, like 3 space, 1 time.
Could be perfectly described by a totally different theory that doesn't even have gravity in it and lives in only 3 dimensions.
That's the claim.
That sounds impossible.
Huh.
A cosmic magic trick. What does that even mean for gravity?
Well, this is why it's so revolutionary. The implication is monumental. Gravity might not be fundamental in the way we usually think, meaning it could be perfectly described by a theory that doesn't include it at all, just in a different dimensional setting. It forces us to ask, what is gravity, fundamentally? Is it a basic force like electromagnetism? Or is it an emergent phenomenon, something that arises from the collective behavior of simpler things in a lower dimensional system?
Like temperature emerging from atoms moving. Gravity could emerge from what? Quantum particles in fewer dimensions.
That's the idea.
Yeah.
Perhaps it emerges from the quantum entanglement of particles in that lower dimensional field theory. It's a profound suggestion.
So if gravity is emergent, it completely changes how we search for a theory of quantum gravity, doesn't it? We've been trying to quantize gravity.
Right, trying to treat the gravitational field itself as quantum. But if gravity isn't fundamental, maybe that's the wrong approach. Maybe the true quantum theory lives in that lower dimension, and gravity is just what it looks like from our higher dimensional perspective.
That opens up entirely new avenues.
Wow. And the dimensionality aspect is key here too, right? The article mentions the extra dimension in the gravity theory might be emergent, like a hologram.
Precisely. That's the holographic principle connection. Think of a 3D hologram. You see a 3D image, but all the information is stored on a 2D surface, the plate.
Right.
ADA CFT suggests something similar for the cosmos. Maybe our 4D space-time with its gravity is a kind of holographic projection.
A projection from what?
From a quantum field theory living on its boundary, in one less dimension. That extra dimension in the gravity theory isn't fundamental in the usual sense. It's more like a mathematical construct that emerges from the boundary physics.
So our 3D space, the one we live in, might just be an emergent artifact, a projection from some deeper, lower dimensional reality.
That's the mind-bending implication. It challenges our intuition that our 3D space is the ultimate stage. If the universe is holographic, the physics on the boundary in fewer dimensions might be just as real, maybe even more fundamental. So the very idea of a dimension becomes much more fluid, more interconnected.
Exactly. It suggests our basic assumptions about the structure of reality might be, well, profoundly incomplete.
Okay. My brain is officially doing somersaults. And if that wasn't enough, there's another duality from string theory. T-Duality. This one messes with our idea of size.
T-Duality does, yes.
Mhm.
It gives another deep insight into dimensions, especially at tiny scales. So, context. String theory often needs extra spatial dimensions beyond our three.
The ones curled up really small.
Exactly. Compactified into tiny loops, way too small for us to see directly. T-Duality operates in this context.
Okay, so these tiny hidden dimensions, what does T-duality say about them? How does it mess with small versus large?
T-Duality says this. For a string, the fundamental vibrating thing in string theory, not a point particle moving in a small circular dimension.
Okay, a tiny loop.
It behaves identically to a string moving in a large circular dimension.
Small is the same as large. How?
With a condition. You have to swap two key properties of the string, its vibrational harmonics and its winding modes.
Okay, need to untack those. Vibrational harmonics, winding modes.
Think of a guitar string again. Plug it, it vibrates in different ways. Those are harmonics, different energy levels. A string in a curled up dimension can vibrate like that too.
Got it. Vibrations. What about winding modes?
Since the dimension is a circle, a loop, the string can literally wrap around it.
Like a rubber band around a pipe.
Exactly. It can wrap once, twice, many times. Each wrap costs energy. It's a different state for the string. Those are the winding modes.
So a string can vibrate along its length, and it can wind around the dimension. Two kinds of states.
Right. And T-duality reveals this amazing equivalence. A string vibrating a lot but not wound around a small dimension behaves exactly like a string that's wound many times but vibrating less around a large dimension if the sizes are reciprocals, like R and 1R.
Whoa. So if you're a string, you can't tell the difference between a tiny dimension, radius R, and a huge dimension, radius 1R, if you just swap how much you're vibrating versus how much you're winding.
Precisely. The physics is identical, which suggests something incredible.
What?
That at these fundamental scales, the very distinction between small and large might just vanish. Size becomes ambiguous.
No real difference between a tiny dimension and a huge one for a string. That really messes with our sense of scale.
It completely undermines it at that level.
So if distance and size become ambiguous, or maybe meaningless down there, does that give real physical backing to the idea of a minimum length, like the Planck length we hear about?
Exactly. It points towards that. The Planck lengths might not just be the smallest thing we can currently measure or the limit of our theories.
But the smallest physically meaningful distance.
Potentially, yes. Below that scale, our usual ideas of space, of geometry as smooth and continuous, might simply break down. The math we use, based on infinite divisibility, might just stop working.
So space isn't infinitely divisible. Is it granular, like pixels, or even weirder?
That's the huge question. Granular is one picture, like pixels. You can't zoom in further. But it could be stranger. Maybe our math of smooth manifolds just isn't the right tool at that scale.
What replaces it?
Active research. Could be non-commutative geometry, loop quantum gravity ideas, where space emerges from a network of relations, not a smooth background. It signals a radical shift from classical geometry.
Wow, okay. These examples, uncertainty linking position and momentum, gravity maybe emerging from lower dimensions, dimensions losing their size, they are truly mind-bending. They shift everything.
They really do, from particles to space-time itself.
But what does this mean for us, for our reality, the one we experience, the one that feels so solid? How do these dualities affect our philosophy, our idea of what's real?
This brings us right to a key insight, heavily emphasized by Sabine Hassenfelder, whose work guides our source article.
Okay, what's the insight?
She argues that dualities powerfully reveal that our experience of reality is deeply, perhaps inextricably, shaped by our constitution as human beings.
Meaning our biology, our evolution, our brains basically filter reality for us.
Exactly. Think about it. We evolved on Earth in a specific environment. Our senses, our brains, our survival instincts, they're tuned for macroscopic objects moving in 3 dimensions.
Lions and berries, like you said, not quantum foam.
Right. We perceive the world mostly in position space. We track things, we measure distances here versus there. That makes position space feel fundamentally real to us. It's our operating system.
But physics, through duality, is telling us that other descriptions, momentum space, the lower dimensional boundary in CFT, the opposite size dimension in T-duality, are just as valid, just as fundamental.
Precisely. So our human intuition, honed for survival on the savannah, isn't necessarily a reliable guide to the fundamental nature of the universe. It is. Theories that seem weird, alien, counterintuitive to us aren't necessarily less fundamental. They're just not intuitive to us, because our senses and brains are adapted to a very specific slice of reality.
We see the universe through human-tinted glasses.
And dualities show us that while those glasses are useful, they might hide other equally valid, profoundly different views of the same reality.
It sounds almost like reality is relative to the observer's framework, not in a trivial way, but deeply. And the source pushes this with the alien speculation idea.
Hassenfelder's alien thought experiment is brilliant for shaking us out of our human-centric view.
What if aliens evolved differently?
Exactly. Imagine a species with totally different senses or brain structures. Maybe they perceive frequencies as directly as we perceive locations. Maybe they naturally live in what we call momentum space or navigate extra dimensions easily.
They would build a different physics.
They might construct an entirely different yet mathematically equivalent picture of physics. A reality that makes perfect sense to them forms their technology, their intuition.
But would seem utterly bizarre, maybe incomprehensible to us.
And maybe our position space view would seem clumsy and weird to them.
That's powerful. It forces us, the listener, to question if our science, our truth, is the only one. We assume any intelligence would eventually arrive at our physics.
But duality strongly suggests maybe not. Maybe our reality is just one valid interpretation, one useful model among potentially many others.
Not that reality isn't real, but that it's describable in fundamentally different, equally valid ways.
Exactly. It's profoundly multifaceted.
Okay. This has been an incredible tour through some really deep ideas. Let's try to pull together the key takeaways from this deep dive into duality. What should we really hold on to?
First, and maybe the biggest shift in thinking, is that reality might not be uniquely describable.
Multiple valid ways to tell the same story.
Exactly. Dualities show us these multiple, mathematically solid, interchangeable representations of the same underlying physics. Reality isn't illusory, but it's like a gem with many facets. Each facet reflects the light differently, beautifully, truly. No single face is the gem.
Okay, takeaway one, multiple valid descriptions. What's next?
Second, building on that, maybe asking if things like particles or strings or even dimensions are real in some absolute singular sense. Maybe that's just the wrong question.
What's the right question then?
Perhaps the more fruitful, more scientific question is, are they useful models?
Useful for what?
For describing what we observe, for making accurate predictions, for pushing our understanding forward. If a model works consistently, explains things, predicts new things, it's doing its job brilliantly.
Regardless of whether its components feel real to our human intuition.
Exactly. It shifts focus from what is ultimately real to what models work best. It's about effectiveness, predictive power.
Which leads right into the third takeaway.
Yeah.
The practical power of dualities for physicists. They aren't just philosophy.
Oh, absolutely not. They're incredibly powerful tools, day-to-day tools for theorists.
How so?
Dualities let them switch perspectives on really hard problems. Imagine a calculation that's impossibly complex in one theory, maybe involving strong forces. Very messy. Its dual theory might describe the exact same physics, but in a way that's much simpler, maybe weak forces, or a different geometry where calculations are easy.
Like translating a hard geometry problem into algebra.
Precisely that kind of move. This flexibility lets them tackle problems about quark-gluon plasmas, black holes, things that would be intractable otherwise. It unlocks breakthroughs.
Okay, so it's crucial for physics research. But why does this matter to everyone else, to you, the listener?
Because these ideas aren't just for physicists. They encourage all of us to critically look at our own assumptions about the world.
Our ingrained perceptions.
Yes, to realize that what feels real or intuitive to us is often just one way of looking at a universe that's far richer, more complex, more multifaceted than our everyday experience suggests.
It's a call for intellectual humility.
I think so. A reminder that our human viewpoint, while essential for us, isn't the only valid description of reality.
And that's an invitation to keep asking questions.
Absolutely. An invitation to perpetual curiosity.
So we've journeyed through how duality shows us these different yet equally valid pictures of reality, pushing us to question space, time, gravity, even what real means.
Showing the deep connections between physics that looks totally different on the surface.
Which leaves us with a final thought to ponder.
If our human-centric experience, our physics, is just one useful model among potentially many mathematically equivalent ones, what other realities are out there?
Perfectly valid, perfectly predictive.
But just beyond our current human grasp, our intuition. What if a fundamental building block for us, a particle, a field, a dimension, is just a convenient description for us, for our type of mind?
It leaves you wondering, doesn't it? A sense of profound possibility.
Exactly. What else is out there waiting to be described?